Okay, let's start for the today's tutorial session. So I'm Priyanka Agarwal, a PMRF scholar at Chemical Engineering Department at IISc Bangalore, and I will be taking these problem tutorial sessions for the course Differential Equation for Engineers. So we are in week 3 today. So let's begin with the first problem, which is among these four options, which two functions have a non-zero Wronskian? So Wronskian has already been taught in the course, which is W equals to y1 y2 prime minus y1 prime y2, where y1 and y2 are the solutions of differential equation. Okay, so we look at the first case. So we have a 2 into e to the power 2t, let's call it y1, and 3 into e to the power 2t, which is y2. Now, one of the property is that if Wronskian of the if this Wronskian is 0, that would means that the solution y1 and y2 are linearly dependent. Now, if y1 and y2 are linearly dependent, then also the Wronskian will be 0. So in this case, if we see if y1 and y2, they are dependent on each other, that is, if we, let's say we write alpha 1 y1 plus y2 equals to 0, then this will come alpha 1 2 into e to the power 2t plus 3 into e to the power 2t equals to 0, and hence alpha 1 comes out to be minus 3 by 2. Therefore, what we can say is that y2 can be written as 3 by 2 times y1. Thus, these are linearly dependent, and therefore the Wronskian will be 0. So, definitely this is not the answer. Now, if we look for the next part, which is e to the power t and e to the power t minus t0. Again, if you see, this is e to the power t and this is e to the power t divided by e to the power t0, which is some constant. Therefore, again, these two are linearly dependent and the Wronskian will be 0. Now, let's see the other case. Sin t and sin t minus pi by 2. Now, this can be written as sin of minus sin of minus pi by 2 minus t, and this will become minus sin of pi by 2 minus t, and which is minus cos t. Okay. Therefore, now these are now sine and cos functions. Therefore, these are linearly independent, and therefore the Wronskian will be non-zero. So this is the correct option. In this case also, if you see, this can be written as a minus sine t. So these are dependent. So this is the correct answer. Now let's move on to the next problem. it's given that x equals to x1t and x equals to x2t are two solutions of a homogeneous linear second order ODE. Now, which of the following functions is generally not a solution? So, we know from the properties of the solutions that if these two are the solutions, then any linear combination of x1 and x2 should be a solution. So this is a linear combination, so this is solution. This will also be a solution and this is also a solution, but this option does not satisfy these properties. Therefore, this will not be a solution if x1 and x2t are solutions of a given homogeneous differential equation. So this is the right answer. Basically, the principle of superposition, it does not apply in this case. Okay. Now in this question, we have to find which of the following ODEs has a characteristic equation with complex conjugate roots. Okay. So in case 1, now first to find characteristic equation, what we have to do? We have to substitute solution is e to the power lambda t. Okay, and so in case 1, what will it become? E to the power lambda t, lambda square plus lambda e to the power lambda t plus e to the power lambda t equals to 0. So the characteristic equation will be lambda square plus lambda plus 1 is equals to 0. Now we know that for any quadratic equation, ax square plus bx plus c equals to 0, if we find we get complex conjugate roots, p square minus 4ac is less than 0. So in this case, p square minus 4ac will be 1 minus 4 minus 3. So this is less than 0. So we will get complex conjugate roots. Now let's look at the second part. So the equation is this. Now again, if you find characteristic equation for this, it will be lambda square plus lambda minus 1 equals to 0, and the characteristic, so this is the characteristic equation. So in this case, p square minus 4ac will be 1 plus 4, which is 5, and this is greater than 0. So in this case, we will have positive roots, not the complex conjugates. So far we know that this has complex conjugate root, this doesn't. And the next is x double prime minus x prime plus x equals to 0. So in this case, the characteristic equation will be lambda square minus lambda plus 1 equals to 0. And if we check this, it will be 1 minus 4, which is again less than 0. So this will also have complex conjugate roots. Now let's look at the fourth equation, which is x double prime minus x prime minus x equals to 0. So this characteristic equation will be lambda squared minus lambda minus 1 equals to 0, and that would mean b square minus 4ac equals to 1 plus 4, which is greater than 0. So this does not have complex conjugate roots. So this is the correct answer. Okay. So the next question is that we have to solve this equation x double prime plus 5x prime plus 6x equals to 0 with the given initial condition that x 0 is 2 and x prime 0 is 3. So let's try to solve this equation. So what we notice is that this is homogeneous and linear equation also. So we can assume that let x equals to e to the power lambda t be a solution of this equation. So characteristic equation for this will be, so if this is x, then x prime will be lambda e to the power lambda t, and x double prime will be lambda square e to the power lambda t. So characteristic equation will become lambda square e to the power lambda t plus 5 lambda e to the power lambda t plus 6 e to the power lambda equals to 0. Taking e to the power lambda t is common. So 5 lambda plus 6 equals to 0. Now this is the quadratic equation in lambda which we have to solve. Yes. Okay. So here the value of lambda can be written as minus 5 plus minus square root of b square, that is 5 square minus 4 into 6 over 2. So the roots will be minus 5 plus minus root 1 over 2. So the roots become minus 3 and minus 2. So therefore what we know that the general solution of this equation can be written as a constant into e to the power minus 2t plus another constant c2 into e to the power minus 3t. So this is the general solution. which we have. Okay, so yeah, now we can use our initial conditions to find the values of the constant C1 and C2. Okay, so initial condition says x of 0 is equals to 2. So this will be 2 equals to C1 plus C2. This is one equation which we get. And from the other, which is x prime of 0 equals to 3, then we will get 3 equals to differentiate this, then this will be minus 2 into e to the power minus 2t. So basically this is x prime plus c2 into minus 3 e to the power minus 3t. So x prime of 0 is 3, so it's 3 minus 2c1 minus 3c2. So now we have to solve this and these two equations, and we can find the values of C1 and C2. So from this equation we can write C1 as 2 minus C2 and substitute here, so it will be minus 2 minus C4 plus 3C2, and this will be minus 4 plus 2C2 minus 3C2 equals to 3, and so this gives C2 equals to minus 7, and therefore C1 will be 2 plus 7, which is 9. So the final solution will be x of t is 9 e to the power minus 2t. It's minus 7 e to the power minus 3t. Okay, so let's move to the next question, which is find the solution of x double prime minus x equals to 0 with the given initial conditions that x of 0 is x naught and x prime of 0 is u naught. Now again the first step would be to find the characteristic equation. Now we know that this equation is homogeneous. So the characteristic equation will be lambda square minus 1 equals to 0. Simply if we substitute x equals to e to the power lambda t, we will get this characteristic equation. So in this case the roots will be lambda equals to plus 1 and minus 1. So the general solution can be written as x of t is c1 e to the power lambda 1t plus c2 e to the power lambda 2t. Now these are the values of lambda 1 and lambda 2. So we can write it as c1 e to the power t plus c2 e to the power minus t. Right? So this is the general solution. Now we have to apply the initial condition. Which is x of 0 is x naught. So this will mean at x0 equals to C1 plus C2. So this is our first equation, and the other initial condition is x prime 0 equals to u0. So this would mean x prime is C1 e to the power t minus C2 e to the power minus t. Simply by differentiating this, we get this. So now if we use this initial condition, we will get u0 equals to C1 minus C2. Now these are the two equations, and if we solve equation 1 and equation 2, so to solve we can add with the equations. We will get value of C1 is x0 plus u0 over 2, and value of C2 can be written as x0 minus C1. C1 is x0 plus u0 over 2. So this will become x0 minus u0 over 2. So now we have got the values of C1 and C2, and if we substitute it in this particular subgeneral solution, we will get our final solution. Now let's do that. Okay, so x of t is now x0 plus u0 over 2 into e to the power t plus x0 minus u0 over 2 into e to the power minus t. Now if we take x0 as common, we get e to the power t from here and e to the power minus t from here over 2, plus if we take u0 as common, we can write e to the power t, and from here minus e to the power minus t over 2. Now these are some familiar forms and can be expressed in sine hyperbolic and cos hyperbolic functions. So basically we can write this as cos hyperbolic, and this can be written as sine hyperbolic. So therefore the final solution will be x0 cos hyperbolic of t plus u0 sine hyperbolic of t. Okay. So let's try to solve another question, which is x double prime minus 2x prime plus 5x equals to 0 with the initial conditions given as x of 0 equals to 1 and x of prime at 0 equals to 0. So again, in a similar way, we can write characteristic equation for this. So the characteristic equation will be, simply we substitute x equals to some e to the power lambda t, we will get it, and this will give us lambda square minus 2 lambda plus 5 equals to 0. Now in this case, roots will be minus b, which is minus of minus 2 plus minus square root of b square, which is minus 2 square minus 4ac, which is 4 into 5 into 1 over this. So this will be 2 plus minus under root of minus 16 over 2, which again is 1 plus minus 2 iota, right? So this has been taught in the lectures how to deal with such roots of the characteristic equation, how to write the general solution for this. So basically, the simplest way is to write it as x equals to x of 2 is c1 e to the power lambda 1 t plus c2 e to the power lambda 2 t, and here in this case lambda 1 will 1 plus 2 iota and lambda 2 will be 1 minus 2 iota. So the solution becomes c1 e to the power 1 minus 1 plus 2 iota into t plus c2 e to the power 1 minus 2 iota into t. So this will become, if you take e to the power t as common, c1 e to the power iota 2t plus c2 e to the power minus iota 2t. Now please note that this can also be written in the form of sine and cosine functions. So this will become, can also be written as e to the power t, some other constant a cos 2t plus another constant b sin 2t. Basically, if we write these in the form of sine and cos, we will get the addition of these constants and the difference of these constants, and we have given them the name of new constants. So this is our general solution. Now we have to use these initial conditions given in the question to solve this problem. So first condition given is x of 0 is equals to 1, which means that in this equation if we substitute t equals to 0, so e to the power 0 is 1 and a cos 0 is 1 plus b sin 0 is 0 equals to 1. So this directly gives us a equals to 1. And the other initial condition is x of prime at 0 equals to 0. So this would give, now we have to find x prime did this happen. Okay, so x prime will be e to the power t as common, So this is x1. So differentiate this with respect to t. So it will be 2 minus 2 sin t to t plus 2e cos to t, and now e cos 2t plus e sin 2t into differential of e to the power t is e to the power t. Now x prime at 0 is equals to 0, which gives us 0 equals to sin 0 will be 0, e to the power 0 is 1, cos 0 will become 1. So it is now 2b plus, from here cos 0 is 1, a. Now we know the value of a, which is 1. So therefore b is minus 1 by 2. Now we have the value of both a and b. This can be substituted in this equation, and the final solution can be written as e to the power t into cos 2t minus 1 by 2 sin 2t. So this is the final solution. Okay. So in the lectures, Professor Manam has already taught this method of variation of parameters. So I will quickly revise this so that it's easier for the next problem to attempt. So y double prime plus p of xy dash plus qxy, if this is the given differential equation of second order, and this is non-homogeneous. In case of non-homogeneous, we have to find particular solution also. So how do we solve this? That is, first we find homogeneous solution, which is, let's just assume that this term does not exist and equate it to 0 this left hand side, and we get this. And for this we already know how to solve these equations, and we have already done few examples now. So we know how to solve this, and we will get the homogeneous solution. Now we have to find a particular solution which should satisfy this, and therefore the particular solution will be somewhat this form, where this c1 and c2 can now be written as a functions of x. So let this be the solution. We differentiate and consider that this term is 0, and then substitute the value of pi p dash and pi p double dash in the original homogeneous equation of second order, and when we solve further we get this, that c1 dash y1 dash plus c2 dash y2 dash equals to fx, and this can be written in the matrix form like this. Now when we write it in the matrix form, we know that the determinant of this particular matrix is Wronskian. Now we get Wronskian, and based on the Wronskian we can tell whether the solutions are independent, linearly independent or linearly dependent. Now here our goal is to find the values of this C1 and C2. So this can be written as this. Now we have y1 and y2 from the homogeneous solution. So these values we already know. So when we know these values, then we can find the C1 prime and C2 prime. Simply, it's algebra where we have to solve this set of equation. We can solve it using Cramer's rule or finding the inverse of this matrix and solve. So at the end we will get the value of C1 prime and C2 prime, and when we integrate those C1 prime, this is C1 prime, we get the value of C1, and when we integrate C2 prime, we get the value of C2, and when we combine this, we can write the particular solution. Okay. Now we have revised, so let's solve this question where we have to find the particular solution of this equation. So basically this is given. Now how can we approach this? First and we are already given that this is the solution. That means y1 and y2 are already given. Y1 and y2 are already given, so we have found the particular solution. So simply we can write this particular solution as y into some u, where we can write this yu dash with this function f. So f here is this one 1. Okay, so the first step should be in this is to find the Wronskian. So Wronskian will be determinant of this particular, this particular matrix. So this will be this minus this e to the power 16. Right, so this is our Wronskian. Now once we know the Wronskian, we can write this as so the solution which we know into u, differentials of u goes to the function which is making this equation non-homogeneous. Now we already know the value of y, so using Cramer's rule we can solve this, right? So the solution is going to be u1 prime can be written as 1 by the determinant of y. So this is actually determinant of y also. So it will be 2 e to the power 16, and so the first row we just place 1 and rest 2 rows we just copy. And this becomes e to the power 2t minus into minus 1, which is plus 1 over 2 e to the power 16. and this will be not e to the power minus 40 plus e to the power minus 60 over 2. One prime. So now similarly u2 prime can be found, which will be 1 by 2 e to the power 60, and here the solution will be e to the power 40 e to the power 60, and this comes out to be e to the power minus 2t minus 1 over 2. So now we have u1 and u2. So we can also, now we can write u as u prime as 1 by 2 e to the power minus 40 plus e to the power minus 60. So this is for 1 prime, and u2 prime will be e to the power minus 2t minus 1. So we now know the u prime. Now we can integrate, and when we integrate we can find the u. Integrate, and let's take the constants of integration as 0, find particular solution. So yeah, u will be then 1 by 2. If we integrate this will be e to the power minus 40 over 4 plus e to the power minus 60 over minus 6 e to the power minus 2t over minus 2 and minus t. If we simplify, we can write it as u equals to 1 by 2 . So here yeah, so we can put it in as this. And we know that by particular is y into u. So we know y and we know u, this can be multiplied and we can find the solution. Okay, now let's solve this equation. So the given equation is x double prime plus 5x prime plus 6x equals to e to the power minus t, where we are given that x of 0 is 0 and x prime 0 is also 0. Okay, so again we will approach this problem in a similar way, where we will first find the homogeneous solution and then we will find the particular Sorry, I lost the connection. I'll show my screen again. Yeah. So we have to solve this equation. So let's first find the homogeneous solution. So homogeneous solution can be defined as solution of this equation will be the homogeneous solution, which will be this. So the characteristic equation would be lambda squared plus 5 lambda plus 6 equals to 0, and the roots come out to be minus 3 plus minus 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 ABC 2. So the roots are minus 5 plus minus 1 over 1, which is minus 3 minus 2. Okay, so homogeneous solution can be written as C1 e to the power minus 2t plus C2 e to the power minus 2t. Now we have to find the particular solution. Now particular solution can be written as simply let's consider by particular case C1 is e to the power minus 2t plus C2 is e to the power minus 2t. So we can also solve this equation by writing particular solution in this form, or we can also substitute directly as y equals to like this. So basically we have to now find this. So yeah, in this case we can take right button Wronskian energy, that is by using Kruger's formula we can find the solution because we already know part of the solution. It is going to be similar to what we did in the previous question. So let's not repeat it. Instead, let us take a new form and try to solve it. Okay. So the other question we can take is d to y over 2x square minus 2 dy over dx plus 5y equals 0. So this is a homogeneous equation that we know, so we can apply the substitution that goes to ux into dx. So y dash can be written as u dash of x u plus u of x into u dash of x. And y double dash can be written as u into u double dash x plus 2 into u dash of x into u dash of x plus u double dash u. Now we have to choose u such that in this equation the coefficient of u dash equals to 0. So basically now these three we can substitute. Let's call it equation 1. So we can substitute it in equation 1. So this has already been shown below just how to do it, and what we get as a result is that p of x can be written as c into e to the power minus 1 by 2 integral of dx dx. So in this case px is minus 2 10x. So b of x can be written as c into e to the power integral of 10x dx, which is c into e to the power of 6x. So this becomes some constant into 6x. So therefore now the solution y is equals to u of 6x. We are dropping the constant here as we can consider it in the u. Now once we have written this, so when we substituted all these in the first equation, our equation was something of the form that is u double dash plus this coefficient u dash plus some in this one. This coefficient will be 0 dash plus 2x u over u into u equals to 0. So now this equation is in terms of u. Okay. Now we know v is sec x. So v dash can be written as differential of this, which is sec x from x, and v double dash can be written as differential of this. This will be sec x into sec square x plus 10x into sec x tan x. So if you take sec x as common, it is sec square x plus tan square x. This is 1 So V double dash is also sec of x. Okay. So V double dash over V plus P of x V dash over V plus 2x into V over V becomes V dash sec x becomes sec x is 1, Px we have as minus 2 10x, and V dash is sec x 10x, this will be 10x, and then qx in this case is 1. Right? So this is what we got, 6 minus 2 10 square x. Now the equation reduces to this equation reduces to plus c equals to 0, and the roots of this equation can be found as lambda square plus 6 equals to 0. So lambda will be plus minus root 6 iota, and you can be written as c1 cos root 6x plus c2 sin root 6x. So now we know u and as well as v, and therefore we can write the solution. Okay, so that's all I have for today's tutorial class. If there are any doubts, please let me know. Okay, till today's session, end today's session here. Thank you for attending. See you next week.